Did you get it? Okay. I'll begin. Isaac, we're praying. Be quiet, okay? Dear Heavenly Father, we thank you for this day. Thank you for these students. Pray that you be with us to help us to glorify you what we do, and just to wrap up as we review for this course and the final exam. Lord, in your name I pray. Amen. Yeah, so technically on the syllabus I had something about tensor products and the bookkeeping theorem, and I'm sorry to let you guys down, but I don't have time to get to it at the moment. So you're safe. You play toys. Okay, that's good. Somewhat relatedly, I don't have your test graded yet. Annoying, but true. But I think I should talk to you about the solution to test 3, and so let's do that. Guys, you got to be quiet, okay? Shh. So let's see here. I did glance over the first page, and I noticed most of you will be bored by what I'm about to show you because you got this too. So this matrix 1, 4, 4, 1 is supposed to find eigenvalues and eigenvectors, solve the system of differential equations, and find the formula for a to the power n. So to start with, the characteristic equation is factored into lambda minus 5 times lambda plus 3, which gives us eigenvalues of minus 3 and 5. So then what I have to do is figure out a basis for the null space of those appropriate matrices, right? Isaac, if you want that lollipop, you're going to have to be quiet, man. So a plus 3i is this matrix. A minus 5i is that matrix. I can just look at these and tell you what vector when multiplied gives you 0, right? Like it's pretty obvious that 1 minus 1 when you multiply it by 4, 4, 4, 4 is going to give you 0, right? And it's pretty obvious that when you multiply 1, 1 on this matrix, you're going to get 0, 0. Isaac, Matthew, if you want that lollipop, you're going to have to be quiet, man. Ahem. Shh. Like a mouse. I tried. Anyway, so any questions about part A? I mean, and then what I do here, I normalize them. Of course, technically speaking, I wouldn't have to divide by root 2 here, like any scalar multiple would do if I'm just looking for eigenvectors. But dividing by root 2 just sets me up for creating an eigenbasis, which is orthonormal. Basically, these are just normalization factors, right? Like 1 minus 1 has length square root of 2, and 1, 1 has length square root of 2. So if I divide by root 2 both places, that makes it a vector of length 1. So I'm just turning them into unit vectors by normalizing. For part B, I don't really care about using the same vectors exactly. So I just forgot about the root 2 because this will do, and it's a little bit less writing. So there's an eigenvector, eigenvalue minus 3, eigenvector, eigenvalue 5. And as we discussed, the solution to the general problem looks like that. Now, and then we did a problem like this in class, right? So, good brothers. That's right. Tell them. So a to the n is a times a times a times a times a times. Well, you get the idea. And so if we can diagonalize a, that means we can undiagonalize the diagonal matrix to give me back a. So like a is beta d beta inverse, right? So I just take that here and I plug it in n times. But you notice what happens in the middle. These cancel, and we're just left with d times d times d times d times d times d times dn times, right? But a diagonal matrix raised to the nth power is easy. It's just, exponentiate the diagonals. So you get that. And then because beta I made orthonormal, the inverse is the transpose. I don't even have to think about it. So I just take the P matrix, and over here is, well, I'm sorry, this is the, technically this is the, anyway, here's your basis matrix and its transpose. And then I just multiply it out, and there you go. That's the nth power. Uh-oh. He's got the dinosaur puppet out. Yes. Dangerous cuteness. Yes, he's that age. So whenever I do a calculation like this, it's got so many steps, I just think it's worth taking a second to check, to make sure I'm right, So I plugged in n equals 1, and I got this, which gave me that, which gave me that, which is a again. So a to the 1 should be a, right? You could check n equals 0 too, right? If I put n equals 0, what do I get? 2, 0, 0, 2. Divide by a half, I get the identity matrix. That's also a good sign, you know? It doesn't take long to check your answer here. It's worth it, right? So here we've got a quadratic form in 3 variables. And we're supposed to find the matrix of Q. So I do that. You see the x squared gives me the 1. Minus 2y squared gives me the minus 2. The z squared gives me the 1. This 6xz gives me a 3 here and here. Remember, I want to make it symmetric so I can use the real spectral theorem, which is, you know, where the fun is at. And then, of course, the absence of xy or yz puts zeros here and here, right? And I gave you a hint that lambda equals to 4 is something you should factor out. I don't think I ended up using my own hint because when I calculated the expansion, when I calculated the expansion, it just stuck out to me that there was a common lambda plus 2 term in both places. So I factored by grouping, pulled out the lambda plus 2. Yes?
Okay. I also have my questions later.
So my question is, what property you said it's symmetrical, so you can just multiply? Or
I want to make the matrix symmetric because that way I know I can find an orthonormal eigenbasis and all the eigenvalues are real.
so to find the eigenvalues, you just did normal to determinant.
Right. To find the eigenvalues, I calculate the characteristic equation of the matrix,
Okay.
which is what I'm doing here. What's your question on? Your question?
For the eigenvalues,
Yeah?
how do you know which one to choose for the Q?
For the Q,
Like
I have to use all of them.
no, I know, but what is the
Which one goes first?
yes?
Oh, that's up to you. There's many orderings possible.
Yeah, but there's only one correct one when you apply everything back together, right?
Well, I mean, the order matters. If I'm actually finding explicit formulas for x bar, y bar, z bar, then whatever eigenvalue goes with the first eigenvector is the one that comes first and so forth. But like here I haven't found eigenvectors, right? I've just found that my eigenvalues are minus 2 repeated and 4. So I could just as well write down what I wrote, or I could write down, for example, minus 2x prime squared plus 4z prime squared minus 2, plus 4y prime squared minus 2z prime squared. You know, I mean, you can move the numbers around. It would be the same formula.
If you find the formula for x bar, y bar, and z bar, and then use also value to get back to the, wouldn't it not be the original? If the order is not correct, wouldn't it?
Yes. Yeah. I mean, the order has to match the change of basis matrix. That's true.
So you mean that for this question, you basically can just choose whatever?
Yeah. I didn't ask you for those details, but if I was to ask you for those details,
Yeah, that's why in the
it's.
answer I wrote out all the 3 ways.
I see. So that makes sense. I mean, I understand why you would do that. But if we do this, where v1, v2, and v3 are eigenvectors of A, then that will be equal to lambda 1, lambda 2, lambda 3, like that, yeah? Assuming that AV1 is lambda 1 v1, AV2 is lambda 2 v2. If I had that, this is the similarity transformation, which would get me to that particular diagonal matrix, right? And then x bar, y bar, and z bar wouldn't be up for grabs. X bar would go with lambda 1, y bar would go with lambda 2, z bar would go with lambda 3. Everything else being the same, yeah? Anyone else have a question?
I'm just how you found Q.
Oh.
Anything else I'm pretty clear on?
Best thing to do there is to find another one. So suppose we had q of x, y, z equal to 3x squared minus 7y squared plus 4z squared plus 2xy plus 10xz minus 3yz. Right? Oh, yeah, I made up a different one. So what would the matrix of Q be here? So they're like, you put the 3, the minus 7, and the 4. That's from this, this, and this, right?
1, 1, and
Then
then
the this xy term here, that leads to putting a 1 here and here. Take half of it. Then this xz, put the 5 here and here, and that would lead to minus 3 halves and minus 3 halves. Now, the proof is in the multiplication, really. I mean, the question is, if I take Q of V and I try V transpose matrix of QV, do I get back to that formula up there, right? And so you can multiply it out and check that what I'm telling you is right. I mean, it is. Now, I think if you have been studying Shor carefully, he might do something more like this, generically speaking, right? And put zeros down here. So he might use like an upper triangular matrix. And if he does that, then he doesn't have to divide by 2. I mean, it is true that you could make the matrix 3, 2, 5, minus 7, minus 3, 4. And if I take this times xyz, row vector, times xyz, column vector, what I'll get is 3x plus 2y plus 5z minus 7y minus 3z and 4z. Multiply that, I get 3x squared plus 2xy plus 5z squared minus 7y squared minus 3yz plus 4z squared, which of course is the same thing. So like in principle, you could use a different matrix that wasn't symmetric, but if you do that, then you cannot apply the real spectral theorem, which only for symmetric matrices. So that's why I don't do this. And so this, what I'm trying to say is, this is what Shor does, but I would say this to that. We want symmetric like that. Yeah. It is a choice, though. Any other questions? Yeah.
So is that the same matrix as that then?
The one I just wrote
Yeah.
down, the triangular one?
Yeah.
It gives you the same formula, but it's not the same matrix.
Yeah, sorry, that's what I meant.
Yeah. But yeah.
Okay.
If you drop the insistence that the matrix of the quadratic form be symmetric, then the answer is not unique anymore. Now, if you insisted that the matrix be upper triangular, the answer becomes unique again.
Okay.
But you've always got this, you can always kind of like shift a little bit above and a little bit below
Yeah.
and play this game. You know, you could.
Sorry. So does the 5 then become a 10 or in the upper right-hand corner?
Did I do that? Oh, yes, thank you. Sorry about that. Thank you. That is helpful. 10. Wait, how did I get a 5? Oh, I'm sorry, that's not what that. Doofus. Let's see here. Me, not you. Here, right? Oh, and that was wrong. What was this? I can't multiply. X times z. Duh. 3x squared, 2xy, 10xz. This is y squared, 3yz, 4z squared. Yeah, okay. Sorry. that was helpful. Other questions, corrections, comments? Let me move on here. Number 3 was very much like, this is an easier version of a problem I gave you guys on the mission, right? So on the mission I had like the 2, 2, 2 one with the ones on the, I had this but with 3 2s and 2 1s, right? The 3 by 3 Jordan block. Anyway, so here, what I do is I determine that a minus 3i squared is 0. And I kind of I know that that's going to be the case because, yeah. Oh, lights, yeah, thanks. It's easier to, come on. All right. And I know to do that because I've worked the homework, okay? I mean, honestly. And I've thought about this before, but I happen to know that if a matrix looks like that, if it's a Jordan block, if I take minus 3i, that removes the diagonal piece of it, right? Which we had a homework problem, remember that? The D and the N. I was trying to build some intuition a little bit. The point is, a minus 3i is just an N piece. It's just a nilpotent piece, and so its square is 0. And once I see that, then I can use the magic formula idea. Sneeze. I can almost hear the lollipop staying in the jar. Uh-oh. I could give the lollipop to one of these students. They're being very quiet. I bet they'd like a lollipop. What do you think? All right. This is, so you were in the last class. Isn't this amazing? Quite, I mean, you guys can review the tapes later. This is astounding. So, man, candy's powerful. Let's see here. So a minus 3i is that. Anyway, the point is, I can rewrite e to the ta as e to the 3t times that, right? And so this is a standard trick for the matrix exponential. And once I do that, you see I've got this series of matrix powers. But this is really nice because I know that that matrix is 0 and so are all the higher powers. So all I'm left with is just this and that, which is, by the way, 1, 0, 0, 1 and t times 0, 1, 0, 0, which just gives me this little 2 by 2 matrix 1, t, 0, 1, multiply the e to the 3, 2, e to the 3, t in here. And so then I've calculated the matrix exponential explicitly. It's that. And once I know that, well, then we're pretty much home free because the matrix exponential is a solution matrix. And what that means in particular is that when I differentiate it, it comes back to a times itself. But when you look at what this equation means column by column, it means that every column of the matrix exponential is a solution to the differential equation dr dt equals ar. So I can just pull off the columns of the matrix exponential one at a time, and those give me the solutions that I'm looking for. Now, if the first time you ever saw this was on the test, this would have been a terribly unreasonable question, right? But a couple things. You had a formula sheet, right? And I had a homework problem that was, you were allowed to have a formula sheet. I see confusion. Uh-oh. What is it? Oh, it's just that. Okay, okay. And this was a toned-down version of a homework problem, so I was hopeful it would be reasonable. I haven't graded it yet. Maybe you all got it right, and I'm just... I don't have to grade it. I can just assume I got a lot of stuff going on. I could just skip grading it, you're saying? I mean, just save my time? Yeah. You feel like you did good on this one. Yeah. I wonder how many liberals in college would be willing to share their grades with their fellow students. Let's see here. Anyway, it's an old joke, but it probably means something. Let's see here. Now here, I was super nice to you. I told you that you got this vector, and you got that vector, and you got that vector, and I said to calculate them. So if you can multiply a matrix times a column vector, you're home free. And I said if. There's an if there, because some of you, I think, are still struggling with this. I could be wrong. I hope I'm wrong. I really hope I'm wrong. I hope everyone got this. It's certainly, let's see. Let me restate that. If you didn't get this yet, you should be able to get this on the final, right? Like this kind of thing. Multiply a matrix times a column vector. Anyway, arithmetic aside, we get back the same vector as we started with, but with a minus, right? So this says that v1 is an eigenvector with eigenvalue -1. This says that v2 is just an eigenvector with eigenvalue 1, right? Because multiplying by 8 gets you back where you started. And here I've got twice my original vector, right? So this is an eigenvector. 1 minus 1, 1 is an eigenvector with eigenvalue 2 for A. Matthew, do you not want your lollipop? Okay. Yes, oh, you raised your hand. Very good. What was your question? You want a lollipop. Okay, well, yes. Oh, well, it's not hard to understand Isaac. He really has several major themes. There's candy, Minecraft, at times Pokemon, Transformers or made-up Transformers. And, of course, you got your Ninjago. You got your Nexo Knights on occasion. You got your Teenage Mutant Ninja Turtles, but I tried to discourage that because we don't like Teenage Mutant Ninja Turtles. That's right. You have what? Oh, you have toy, yes. And then for Matthew, the main thing is understanding that he doesn't say C sometimes, so he'll say H instead of C. You have to understand that. So he'd be like, I want... Which ship did you want for your birthday, Matthew? Oh, Batman now. Oh, okay. Interesting. You don't want Clay's ship anymore? All right, never mind. Okay, I digress. Sorry, guys. So if I take those... Now, Batman Lego set. Okay, let's be quiet so I can give you guys a lollipop afterwards. So you put the hat on it. That means I'm turning them to unit vectors and normalizing them, right? So 1 minus 2, 1 has length square root of 1 plus 4 plus 1, which is 6. Square root of 6. This one, 1 squared plus 0 squared plus minus 1 squared square rooted is square root of 2. And this guy has length root 3. So I have to divide by their lengths to normalize them. The reason I'm doing that is so that I have P inversus P transpose. And so then P inverse AP would be equal to that, right? I've forgotten what the question was. Somehow I distracted myself, as is my custom. I think I just said to find a P, matrix P, for which P inverse AP is a diagonal matrix. Now, I haven't actually multiplied it out, but I assure you that will work, right? So you can check me on it if you want, but if I choose my, I think I have neglected to write a very important equation here. What's the equation I'm missing? Actually, this is kind of a deal breaker. I'd take a point off your test if you were missing this equation. I'm sorry, guys. So I should have said one important thing. P is equal to what? Right, the matrix of beta. That's the thing I didn't write, but I should write. Because I also did not write. You notice I did not write that this was V1 hat and V2 hat and V3 hat. You just assumed it, right? But I should actually write that, right? I mean, this is the sort of thing I don't want you to do either. I shouldn't have to guess what things are equal to. You should state them explicitly, right? Just saying. So that's, I think, missing from my current. And then, of course, once you have eigenvectors, you have 3 eigenvectors for a 3 by 3 matrix, you can solve the differential equation dx dt equals ax by just the eigensolution. So, I mean, I'm getting kind of bored of this question. It's almost too easy once you have eigenvectors to write down this solution, right? You don't, Mr. DeMenu, he says it's not boring? It's not boring at all? Okay. But, I mean, it is, to me, it's kind of shocking how simple it is to solve a differential equation if you can just find eigenvectors for the matrix of the differential equation. It's just this simple. It's quite beautiful. The question, yeah?
Yeah. When do you have to normalize the basis? Always?
Well, the reason I normalized it was I didn't really need, honestly, I didn't really need to normalize it here. I was doing it just for sort of best practices. I mean, if I actually was writing out formulas, I definitely would have wanted to do it, because normalizing it means that when I calculate the inverse, all I got to do is transpose that, since this is a, I think these are orthonormal, aren't they? Are these orthogonal? Dot product of this and that is what? 0. How about this and that? I got 1. Oh, is that a minus or a? It's a scratch. What's that scratch? Is that a? If that's a plus, we're in business, because it's 1 minus 2 plus 1, and yeah. Oh, wait a minute. What does A look like to start with? What can you say about this matrix A? You did it. What'd you do? You did it. You did Lego? I don't know what that means. Little. Oh, Batman Lego. That's what you want, Batman Lego? All right. This is a little bit He has some very disconcerting. You like 2 Legos? Yes, Isaac. What's your comment and or question? What? Are we talking about Rayquaza? Can you have a Lego set? I don't know. Do you got money? No, you're getting. I thought you wanted a lollipop. You want to trade for? You want a Lego set instead? I don't know. That seems like it requires more than just being quiet for a class, I think. I don't know. Like a very small Lego set, maybe. I'm not sure. I'm not sure. Oh, you got the 50. You have $15? He has 9? Okay. Daniel's the banker. Let's see here. Look at this matrix. This is symmetric, right? So our theorem was that, you know, well, that's a good question. I guess the theorem was that there exists an orthonormal eigenbasis if and only if A is symmetric. So A is symmetric. That actually doesn't imply automatically that the eigenbasis is orthonormal. You can find a matrix, a 3x3 matrix, and find a basis for it of eigenvectors, and you can have the case that the eigenvectors are not orthogonal. The thing is, you can then run Gram-Schmidt on it and make them orthogonal. But a lot of times when we do it, they're automatically orthogonal. Like these ones are these. If we have distinct eigenvalues, like this, -1, 1, and 2, there's another theorem that says eigenvectors with distinct eigenvalues for a symmetric matrix are necessarily orthogonal. So like if I have eigenvectors with different eigenvalues for a symmetric matrix, those eigenvectors are going to be perpendicular. It's just it's a necessary feature of the theory. On the other hand, if I had like a repeated eigenvalue, say of 4, I could get 2 eigenvectors, both for eigenvalue 4, and they might not be perpendicular. But the thing is, you can run Gram-Schmidt on them and make them into a perpendicular set if you want. Where did that happen in your homework? Where did that? I teach too much linear right now. I can't remember where that happened for me. If it was this class or the other class. Other class? Other class. All right. Let me see if I can find it right quick. It's kind of neat. I mean, it's the other class, but it's relevant to you guys, at least to make sense of what I'm just talking about. Yeah. Humor me for a second here. It's probably their recent homework. I think it's problem 130 for them. Yeah, look at this. This weirded me out because I wasn't aware this could happen when it did, but it's kind of a neat example. This is actually sort of like the one on the test, but with a little bit more asked of you, you know? So here I give you this quadratic form, and I say find the matrix. And for them, I ask them to actually find an orthonormal eigenbasis. Now this is a homework for them. It's not test in 321. Okay, so it's a 321 homework question. But I do that. I find that the eigenvalues are 1 and 10. It worked out pretty nice, actually. And the thing about it is that when you look at eigenvalue 1, which is repeated, and you look at the eigenvectors, well, you get this. I mean, it's pretty obvious that this reduces to that, right? That's a nice one. And so the null space of A minus I looks like this. But look at these vectors. Are these perpendicular like this and that? See these? I can normalize them, right? Fine. Are they perpendicular, though? I mean, the dot product of the first one and the second one is not 0, right? So you're like, wait a minute, I thought you said the real spectral theorem says that a symmetric matrix has an orthonormal eigenbasis. That's right, it has it. It doesn't mean that every eigenbasis is orthonormal, though. This is an eigenbasis, these are eigenvectors, but it's not orthonormal because, well, it's not done, basically. So I go to the next page and, run Graham-Schmidt on those bases for the null space, and I get these two vectors here, I think. These are the Graham-Schmidt of the original null space basis, and that gives me an orthonormal eigenbasis for A, and so forth. So that can happen, but that's like the first time I remember ever running into that in the years I've been teaching linear. But now I know about it, so I guess I could ask about it, but whatever. Let me go back to your test. Where were we? All right. Number 5. Let's see here. I'll tell you what, every time I write the solution for one of these, I just think to myself, why did I assign this? This is going to be awful to grade. But you guys are you're gonna set me right. You're gonna be like, I'm gonna look at yours, and it's gonna be clear what you did, and it's gonna be beautiful, and it's gonna be right, and all of these worries I have as I'm writing the solution are going to go away. It's the power of positive thinking, right? Let's see here. If you believe in that sort of thing. I mean, I don't, but let's see here. I mean, I think prayer has power, but positive thinking is, well, kind of depends on who's thinking it, right? Let's see here. So this determinant gives me that, which gives me that, which gives me, after completing the square, this guy, which tells me 4 plus or minus 2i are my complex eigenvalues. Did you guys get that one? How many people got this eigenvalue? Okay. Yes. All right. So I pick one. I like the plus. So 4 plus 2i. I take A minus 4 plus 2i. That gives me this matrix. Basically, I'm looking for the null space of this matrix, right? Those are my eigenvectors. Non-trivial vectors in the null space of this matrix are my eigenvectors with eigenvalue 4 plus 2i. And so I just pick the equation I like the most, which for me is the second one. It says that minus u is equal to 2 plus 2i times v, right? And pick your value, any value. I'll pick v equals 1. It's nice. That gives me u is equal to minus 2i, and that gives me this lovely complex eigenvector with eigenvalue 4 plus 2i. This is by no means unique. That's the joy of grading this problem, is there's infinitely many correct, different looking answers. So if your answer did not look like this, that does not mean you're wrong. I have to think about it a little bit to see if you're right or wrong here. For me, this is the hardest problem to grade, without a doubt, because complex eigenvectors can look so different. You see, if I had chose v equal to like 3 plus I, this would still be legit, right? I mean, basically, you can take this vector and multiply it by any complex scalar, and that's still a correct answer. If you think about what multiplying by a complex number looks like, it gives you a lot of different things here. Literally any complex number can be in the second component except for 0. Yes, Daniel? Matthew wouldn't stop.
He's asking if he could play with one of my transformers, but I say no.
You said no? You don't want him to play with your transformers? Are you sure about that?
I want to do that.
You what?
I want
You don't want to share with your brother?
to. I do.
Oh, you do? Good decision. Let's see here. Let's see here. So, so this is my complex eigenvalue. This is my complex complex eigenvector with complex eigenvalue that. So again, this is a solution to the differential equation. A little bit less boring, I think. The point is, this is a complex solution, though, right? So I got to peel off its real and imaginary parts to get real solutions. And basically, we need Euler's identity, which is that this is e to the 4t. The e to the 2it gives me cosine 2t plus I sine 2t. And this vector breaks into the real vector minus 2, 1, and the complex vector I times minus 2, 0. Any questions about this? I mean, what I'm writing here? Do you guys understand what I'm doing? So then I peel off the real part of this. The real part of this comes from like the cosine times that, right? And then this I times that I gives me minus 1. That gives me 2 sine t. That's this 2 sine t term. So over here, the imaginary part, I sine t times minus 2, 1. That gives me this minus 2 sine t and this sine 2t down here from this, right? And then this I times cosine gives me the other imaginary piece. And that's why I pick up this minus 2 cosine t here. You could have also written your answer as like cosine of t and sine of t times vectors. I'll count that right just the same. Just for me, this feels like less effort in terms of the writing. So, I do want an answer that has a C1 and a C2 and only real functions, right? I want a real solution. But beyond that, I'm pretty open-minded about how you format the answer. All right, enough about that. Suppose the characteristic polynomial of A is x squared minus 9 squared. So first thing we got to do is factor it. However you like. Of course, this is x minus 3 times x plus 3. This is x minus 3 times x plus 3. So we got 2x minus 3s, and we got 2x plus 3s, right? This tells me that I've got eigenvalue 3 and minus 3 both repeated. And then these are your choices. You can either have the case that is diagonalizable, like so. You can have the case that you have 2 eigenvalues linearly independent with eigenvalue minus 3, but you only have 1 for eigenvalue 3. That's this case. This here says I've got 2 eigenvectors with eigenvalue 3, but I've only got 1 eigenvector with eigenvalue minus 3. And then finally, this case is when I've only got 2 eigenvectors total linearly independent, 1 for 3, 1 for minus 3. And I need 2 generalized eigenvectors to complete the Jordan basis. Now, there is other ways of writing this. Like, I could be silly, and I could put minus 3 up here, and I could put 3 down here instead of this. That would still be a legitimate Jordan form. This one, of course, I could do something silly like, I know it's not that silly. I could switch the blocks, you can always shuffle the blocks around, and I would still say it's the same Jordan form. If you want to remove this ambiguity, you can come up with some kind of nomenclature which insists on putting like the smallest block first and then increasing eigenvalues or something like that. You could do that. And I'm sure software packages which do this have their own particular native rules for setting that up, right? Is that it? This test is crazy short. No?
It was perfect.
It was perfect? Oh, if I know it was too short then. If a student tells me this test was perfect, it was definitely too short.
Maybe like perfect time-wise.
Perfect time-wise. It was wicked hard.
It needs to be short. Final needs to be shorter than this.
Finally needs to be shorter than this. You guys are a hoot. Tell you what, we've got a couple of minutes left here, right? Let's go back and look at test 1. You guys have any questions about anything? So again, the thing about tensor products and the bookkeeping theorem I didn't get to. I'm sorry about that. I really wanted to. It just didn't happen. Yes, Isaac? Do you have a question about the final? What? Oh, no, you're okay. Thank you for raising your hand. Your lollipop is safe. Don't worry. Let's see here. Test 2. Oh. Oh. You're like, could we forget about that test? No, this is part of the course, guys. Is this the right course? I see. I have. This is very unnerving. I'm sorry about this. This was like, I feel like this was a form of psychological warfare in here that I've taken part against you, and it was not my intention. Is this actually which class is this from?
I think it was I don't remember.
Is this your test, or is this? Am I in the wrong folder? Oh, look. See, this could have been your life. Aren't these problems? Don't they look interesting? They don't? No. Okay. All right. I'll put that away. I'm sorry.
They're interesting.
They're interesting. to look at from a distance. I see here. Okay. I don't know. I don't think these classes are really that different, but opinions vary on whether my opinion matters or not. Now, this was your test, right? Which I had inadvertently put a 3 there. So just a reminder, you do get a page of notes of your own choosing, right, for the final exam, front and back. It's fine with me. You can take 2 separate pieces of paper and staple them back to back if you want. Like, that's also fine. But the key is just 2 viewable sides of paper, okay? Does that make sense? I've had trouble communicating this differential equations earlier. They were confused by this, but, well, mostly just Danica. Mostly just Danica, but we can name names. See here. We love Danica. Let's see here. So any questions about this guy? This one? This is a pretty straight subspace test. The point is you're looking at antisymmetric matrices. So we argue, first of all, it's non-empty. Easiest thing to do is show zeros in there, right? Once you've got the zeros in there, then we pick two elements in the subspace, A and B. And I want to suppose, and C is a real number, I want to show that the linear combination CA plus B is again in the W, right? Really? Okay. We want to show that CA plus B is again in W, so we transpose, use properties of transpose, and we get back to minus C times what we started, right? And so what does that show? Well, that shows that CA plus B is again in W, right? And then by the subspace test theorem, we have proved that the space of antisymmetric matrices is a subspace. Now, what's an interesting... I built a castle for you? Oh, I did that? Oh, I don't remember doing that. You want me to do that next, like when we go home? Oh, okay, interesting. How about this? What if I asked you to find a basis? A booby trap. Oh, yes, very good. Yes, we need that. So what if I asked you to find a basis for this subspace? Could you do it? These are 3 by 3 antisymmetric matrices. How big is, what dimensional vector space is this W? Oh, look, that was number 2. I split these questions, right? So the way you do it, of course, is to pick an arbitrary element, which is A, B, C, D, E, F, G, H, I, and impose the condition for the space, which in this case is transposes minus it. When you do that, that gives you nice equations like A is minus A, E is minus E, I is minus I. In other words, A, E, and I are all 0. And also the off-diagonal ones have to match up to a sign, right? So generically speaking, this is what a 3 by 3 antisymmetric matrix looks like, right? B, C, H, and then minus B, minus C, 8, minus H. So you see that you can rip it apart as a sum of these 3 basic kind of matrices, and these guys are going to form your basis. So you can do a calculation like this for a lot of different subspaces, like find the basis for a subspace is a decent question for the final. Yeah. Yep.
Can you explain the E12 minus E21, or just show me so I can see it?
Yeah, sure. The E12 is this guy, 0, 1, 0. We're working in 3 by 3 matrices, so this is E12.
Oh, I think I see it.
And E21. So that's just a sneaky way of writing the matrix again without actually writing it out. See, like yeah, you're fine. E12 minus E21 is this thing because it's this minus that gives me that matrix. Yeah. Taylor's theorem is such a nice thing to know. If I want to find the coordinates of x squared with respect to beta, so I can, f of x is f of 3 plus f prime of 3 times x minus 3 plus 1 half f prime of 3 times x minus 3 squared. So that allows me to find the coefficients 1, 6, and 9 here with ease. And then the definition of what a basis is tells me the coordinates to the vector x squared are respectively 1, 6, and 9 here. Yeah. Let me stop talking. Is there any question? No? Is beta orthogonal set? Is it orthonormal? So it's orthogonal because dot products are 0. It's not orthonormal because the lengths are respectively root 3, root 2, and root 6. So how do we fix that? I guess we don't, right? You could fix it by normalizing them, right? But instead, I just so this I forget what this was called in here, but this is how to find the components with respect to an orthogonal but possibly not normal matrix basis rather. So like the difference between orthonormal and orthogonal is with orthogonal, I have to divide by these squared lengths here and here and here, right? If the basis was orthonormal, I wouldn't have had to have these pesky factors down here, right? That kind of goes back to your question earlier, Jessica, like why am I dividing by it? It's because I was thinking about possibly solving a related but separate question like this one. So if I normalize it, it sets me up to answer questions like this. But, sometimes when I'm working a problem on a test of yours, I'll just do things that I think are useful, and I forget about what question I'm solving, and then I go back and I go, wait a minute, what's the question I actually asked? And then I finish answering it, which is sometimes why you'll see extra work on my solutions that doesn't seem relevant. Yes, guys, what is it?
Matthew was picking his nose.
No way.
Either it has blood right there.
Uh-oh, let's not do that. We don't want a bloody nose. No. Not today anyway. Maybe some other day. Let's hear. Ooh, look. This one's very boring. I wouldn't ask this. Right? You guys don't like this question. Right? You guys are underwhelmed. I'm just kidding. I think this is probably like the most interesting and perhaps the central applied problem of this course is discovering this and how it, it flows from that discussion of closest vectors and orthogonality and all that. I mean, I think this is, to me, this is one of the high points in the course is just this problem, being able to solve it like we do. But, you take a step back from it, the idea is simply this: if we have a linear model, we feed data to it, it gives us an inconsistent system of equations. We can't solve that, but what we do is we multiply by the transpose of the matrix. That gives us the normal equations, which will be consistent. You solve that, and through the magic of least squares, we find the best approximation to the problem. I say magic of least squares, but of course we have, kind of hopefully peeled back the curtain there a little bit. Any questions about how to do these? You guys understand why there's 1, 1, 1, 1, 1 here? It's because it's always plus c, plus c, plus c, plus c. If we were working with a different model that was like, say, mx plus bx squared or something for some reason, then you would actually have different numbers, everything. It's because it's always plus c and it has no dependence on x, they would always just have plus 1 here. Thought experiment, if I had cx squared, I would put a 4 here, I would put a 1 here, I put a 0 here, I put a 1 here again. if I had an x squared instead of just c, if I had cx squared. Why would you do that? Well, maybe you've got a problem that should have a quadratic as an answer, and you happen to know for physical reasons it has to go through the origin, right? If you want a quadratic through the origin, a general quadratic would have the form mx plus cx squared, basically, right? That would be a quadratic through the origin. Uh-oh. Starting to seem like I'm going to keep some of my... Starting to seem like I'm going to get to keep some of my lollipops. Yes?
That was Matthew.
Oh, it was Matthew. Okay. That Matthew, he's quite the actor. I think you guys generally got this problem and you understood it pretty well. So I probably don't need to test on this anymore. Right? No? It's too late for these jokes. Okay. Joking aside, I might test on anything. I mean, it is comprehensive. Definitely the tests are a good place to start. This problem. Sadness. This problem died. I would like to bring it back. I do want to bring this back in a sense. Like, I should have asked you a decent Graham-Schmidt question on the test. I don't think that actually happened. This was supposed to be your Graham-Schmidt problem, and it went sideways, right? So I didn't take off points on this one. I forget exactly what I did, but it didn't hurt you, this problem, because it doesn't make sense. I provide a counterexample to my data down here. Okay. If you look at my quote-unquote solution, I basically debunk the meaning of the problem, which is somewhat troubling.
You're not going to test on it, right?
Not this problem, but I would like to replace this problem possibly with an actual, honest-to-goodness, decent Graham-Schmidt question, right? For example, find an orthonormal eigenbasis to that quadratic form I showed you from the 321 homework would be an interesting example. I do think you guys know Graham-Schmidt, so you wouldn't mind being tested on it. And larger point here is if I just, pull up my final exam from last time I taught this course, like, I don't know. Guys, I was responsible for the bringing into existence of this course here. Like, this course is my baby. Because I said that we needed a course which was more for engineers, so that engineers would have a course which was applied focus as opposed to proof focus, and I thought that would be healthy for you guys. And also, just because it's not healthy for you to have to take the math, it's a major math course, 321, right? So it has a very different goal in mind than this course. Like, this course's goal is to introduce you into how to use the toolkit of linear algebra to solve problems, right? Now, we have to talk about theory, otherwise you don't really understand the tools you're using. So theory cannot be removed from the course, but it doesn't also have to be the thing you're responsible for mastering either, So you get to use it as opposed to try to the goal of 321 is for not to just use the theory, but to understand it and even how to modify it, We don't have that goal in here. We have a different set of goals. And I've failed you, I think, in terms of the Mathematica or MATLAB aspect of it. It would take me a lot of hours I don't have to do that properly. I think Dr. Smith is doing a very good job as it stands. And so I'm very happy I had that project to share with you guys. Long term, I'd like to see the course like half of that, half about that. That's what I'd like to see this course become, like half computer work, I think that would be healthy. But easier said than done. Anyway, so this is a pretty standard problem. Here's a matrix, find the basis for the column space and for the null space. Can you guys tell me a different interpretation? What would the basis of the null space also be? What does that mean, the basis for the null space? Can you tell me what other significance the basis for the null space is here? That would be the definition. This is a vector such that that times A is equal to 0, true. My question then, let me ask a slightly more pointed question. how geometrically is this vector, minus 1, 1, 0, 1, related to the rows of A? How is this vector related to the rows of A? What is it? Can you say anything special about the relation here between these rows and that, if you think of this as a row vector for just a second? Or if you like to, think of this column vector and the transposes of the rows. They will form a linearly independent set, I think, but that's coincidental here. There could be a linear dependence amongst the rows themselves in principle. Let me start you out here. What's the dot product of this with 1, 1, 0, 2? Minus 1 plus minus 1 plus 0 plus 2. Minus 2 plus 2, 0. How about this and that? What's the dot product? I got minus 2 minus 1 is minus 3 plus 3, 0. So if you look at this, this vector is perpendicular to the transpose of the rows, right? And that goes back to something that we talked about, which was if I want to calculate the perp to a set S, what do? I calculate the null space of the matrix of S, what? Transpose. So anytime we calculate a null space, we're actually finding a basis for the null space will be a set of vectors, right? Which are perpendicular to the row vectors which you're finding the null space of. It's not an accident that this vector is perpendicular to the rows here. That will happen. That has to happen. If you missed number 9, shame on you. I'm sorry, but come on. Let's see here. Well, I guess anyway. You don't remember any of these problems? Yeah, it's been a long semester. Let's see here. Remember the inner product on C3, it's not just multiplying component against component. We also have to take into account the conjugation, right? So the inner product of Z and W on C3 is W dagger Z. This is what? This is the transpose conjugate. So I take this column vector Z, I turn it into a row vector, that's the transpose, and then I conjugate. So that 1 plus what? Oh, I'm sorry, I'm reading wrong. W. So turn that into a row vector and then conjugate. So I goes to minus I, 2 plus I goes to 2 minus I goes to minus I goes to I. Complex conjugation, right? And then multiply, and we get 5. I think a lot of you got this one, although your notation was a little bit fuzzy. If you had something wrong about notation here, if I fussed about notation here, you should take 5 minutes to fix that so that doesn't get you again. Okay? Like, anyway, shut up, I'll shut up. Let's see here, where else were we? Oh, I guess I did have a Gram-Schmidt. Here it was. Was this on the test? Did I shorten this? Or was this actually part of your test? Okay. I guess this test was kind of long, huh?
Now you realize it.
Not really. If you compare it to historical trends, it's about the usual. Now I realize it. Let's see here. I guess I did give you guys some extra time, but where were we? Unfortunately, with the final, we're stuck with the 2 hours. It's kind of like, it's pretty rigid, the 2 hours in the final, because I've got different people taking different classes at different time periods, so I have to maintain a uniform standard, so I got to go 2 hours in all the finals. You're like, so the final will be short then? I'm like, I didn't say that. It'll be reasonable. How about that? This much we can say. You guys will probably take the same final, so at least it'll be fair. Let's see here. Oh, anyway.